certain processors have a lot of stages, like 100 stages. So it depends on the design. Anyhow, so it's a five pipeline stages, resulting in 5 times improvement in clock frequency. How is this possible? We will investigate the way too. But again, using clock frequency, we synchronize the hardware component, right? And then what pipeline design does is that it actually divides one hardware component into 5 different hardware components. Then what each hardware component needs to do 20% of its original work. Why? Because we divide one hardware component into 5 small components. So then what? We actually need 20% of original clock cycle. Why? Because we divide one work into the subtask, and the subtask is just 20% of the original task. So that what? We only need 20% of the original clock period, which means what? We can increase the frequency 5 times. So that's what's done. Why we use pipeline. So, however, since you need to make the instructions more standardized and simpler, so you end up with twice as many instructions to represent a typical program. This also happens to. We cannot simply divide any hardware component, and also particularly if a hardware component is really complex, then what? It's not easy to divide it into smaller components. So that what, however, if we make the instructions more simple, then what is easier to divide, to process, and the component which process the instructions. So in addition, imperfection in the pipeline due to dependencies, cache misses, resulting in lower efficiency of the throughput. So this one also we will study in this course too, by the way. So in fact, this question actually includes many discussions, so we will study in this course in the future classes. So they are all resulting in 25% increase in the number of cycles needed to execute an instruction. So what's happening is this. So we believe that if we make some like the pipeline the processor, then what? We can improve something like maybe the 5 times the kind of performance we expect. However, what we get is much less than our expectation. Because the reason is because of this kind of difficulties, like dependency problem, and also memory latency, such kind of other factors influence our speed up. So what? Eventually, what we get is much less. So here, this question actually asks this. So okay, then how much speed up we can get? Then what we will come back to calculate, to solve this kind of questions. We have to we come back to our original discussion, right? So what execution time we have to think about? CPU time. So this is CPU time, right? Is what? Again, IC, CPI, CT. Here, right? And then here what? Since we now employ the pipeline processor, so what? This one, CT, became 1/5, right? That's actually our assumption here, right? So what we were able to improve clock frequency 5 times. How did we get that? Again, it's because we have one single hardware component. This operates every cycle. However, what we did is that we divide this hardware component into 5 different sub-components. Right? And then what then we originally needed to process this, maybe the 10 nanoseconds, for example, to complete this hardware component. But then what? Now we only need 2 nanoseconds. Something like this, right? So then what? 2 nanoseconds, then 1 over 2 nanoseconds is 0.5 gigahertz, right? So originally we needed 0.1 gigahertz. So I will say megahertz. So originally we needed the 100 megahertz because we need to guarantee the 10 nanoseconds as a clock period. However, now we divide so that what this hardware component into 5 small components. So then what we can make this to, we can increase the frequency to 500 megahertz. Yes?
If you don't mind me asking, it's a little bit hard to see. What is the denominator for the top fraction where it is equal to 500 megahertz?
So the example, so why we need the where this 500 megahertz came from is this is 2 nanoseconds, by the way. So what originally I assumed that we needed 10 nanoseconds to complete this to execute this hardware component. Then what now we divide this one hardware component into 5 different hardware components. So then what each one needs 2 nanoseconds. I mean, though, this is too ideal. You just think that we ideally divide into, but this making exactly 2 nanoseconds is very hard too. But ideally, that's the assumption here, right? So we exactly divide one hardware component into 5 subcomponents. Then what each one needs 2 nanoseconds. Originally, I assumed that we need 10 nanoseconds. Then what? Then we can assume that each hardware component needs 2 nanoseconds. That's also assumption in this question. So then what? That's what's assumed here. So what? Also, so we can increase the frequency 5 times. That's also assumed in this question too. So what I want to say is that, of course, you don't need to think about this, and then you can just directly solve the question. However, these questions actually discusses actual problems we encounter when we implement by trying the processor. That's what I want to say. So it's not just an imaginary problem. We are actually facing this kind of challenges. So what? Okay, then we made by trying the processor. So then what we were able to increase the frequency maybe 5 times. That's actually what we get typically. However, what happens is right, but the instruction count also increased twice. So then what? This one becomes 1/5. However, instruction count increased to 2 times, right? 2 times. And then also what? Some inefficiency happens here, right? So then what? 25% increase in the number of cycles needed to execute an instruction. What does it mean? Our CPI also increased by 25%, right? So then what? This one also increased 25%. So then what? The execution now, what's the new execution time? So then what? 2 pi 1.25 pi, and then what? This is the original, right? Execution time. So then what? 2.5, 0.5, right? So this one is 2.5 multiplied 1/5 is 0.5 pi original execution time. So then what? We can get twice better performed CPU for here, this design. So then what, how much speed up did you get? Is speed up is original over U, right? Execution time. So then what? This is 2. This is how you solve similar types of questions. And then what? Also the what happened here is this too. So first we implemented a pipeline processor. So what the later chapters what we will do is this too. Like we first implement pipeline processors. Then what we expect the certain level of the performance increase. However, what's happening is that what we gain is much less than what we anticipate. So, for example, once we implement five pipeline stages, then what we expect 5 times improvement. But what we get is maybe 3 times. Then where the other where this inefficiency happened. So the first is instruction maybe. However, I mentioned right, like the instruction we do not discuss much in this course. And the second the major problems we discuss in this class is the CPI, right? So what dependencies, caches, and also the cache state and some other factors we discuss. So this is homework number 1. So maybe homework number 2 also interesting too. So suppose that we put in a complicated fast floating point unit that speed of floating point operation 2 times, and the floating point operation takes 20% of the original. So again, when you solve these questions, we consider this, right? Execution time is IC, CPI, CT, right? So here, what happened? So what floating point operation? So this floating point operation, the CPI. Yes.
If you don't mind me real quick, just could you explain how did you get the 2 for the first question? Like I understand like the formula you used was original.
This one?
Oh no, as the final solution.
Here.
Yeah.
Okay. So this original execution time, new execution time is half of the original execution time. So then what? Original, and then what? Half of the execution time, right? So the time, multiply time, and multiply time. So then what? We delete this time, and then what?
Oh yeah, that makes sense. Yeah. Okay. I appreciate it.
Yeah. Do you have any question here? Okay, sure. So then I'll come back to this discussion. So what? Now the floating point. The CPI of floating point operations becomes half, right? So we don't know the actual CPI, but what we know is that its CPI drops to half. And then also what we know is that the floating point operation takes 20% of the original operations. So then what here the original, we don't know what's the original, but the 0.2 the 20% of instruction now takes half of the time. And then the next, what we can see is that, however, the speed of, so that what resulting in the data cache access. So what the later we will study, but the all memory instructions has to go to so it's maybe I will add more information. So all memory instructions has to go to the data cache first, and then it goes to the memory. So what happens here is this. So what the data cache performance it becomes slowed 50%. Then which means that and then data cache access consume 10% of the execution time. So we don't know what's happening, but the 10% of instructions must go to the data cache, and then but the data cache access is slowed down to 50%. So then what? It's a CPI increase to 1.5 right times. And then the other things is what? 70% of execution we don't know, but it's okay. It's not touched, right? So then what? Frequency also not touched, so we don't need to mention here. So then what? This is the new execution time. What's the old? It's just 0.2, just 1, right? It's just 1. And then again speed up is new over old, right? So then what? This is again the 0.1 plus 0.15 plus 0.7 over 1, right? So then what? 0.95 over 1. No, sorry. This one is when we discuss the time, we have to say that all the execution time over. This is all over. Okay. 1 over 0.1 plus 0.15 plus 0.7. So then 1 over 0.95. This is what? A speed up. So what's the next one? I don't remember. So this one, is the answer too. So you can. What is the overall speed up? Is this one. 1 over 0.95. So around 1.0 something. Do you have any questions here? So the other, there are 10 more questions, and some are, we will study the next week. So you probably cannot do it right now, but yeah. So there are some other questions. So the similar question here, but this one is a little more challenging. So I wanted to discuss in the classroom. So again, suppose that a typical workload will run 40% floating point instruction, 20% the memory instruction, and 40% others. So each floating point 4 cycles, 10 cycles, 1 cycle. So what we actually improve the original machine into with the two directions. So one is design A. So what we do with the design A is that again, design A improve floating point instruction performance to 2 cycles and the memory instruction to 4 cycles. Which means what? We are improving the CPI of the floating point and the memory instructions. So then again we have to calculate the new execution time with design A. So then what here 40%, right? 40%. So here you can assume in this way too. So okay, there is just 100 instructions. Then what? 40% instruction. So 40 instructions is floating point instruction. And then so now it becomes 2 cycles. Right? It's 2 cycles. So originally it's 4, but and then the 20%, right? 20%. So 20 instructions takes now 4 cycles. Plus others takes 1 cycle. So then what new execution time is 80, 200. So original, maybe we can say originally it's 44, 8, 1, right? So originally it takes 160, 60, full cycle. This is 10 cycles. So originally it takes 400 cycles. For example, if a program consists of 100 instructions, then what? Originally it takes 400 cycles. But now with design A, we get 200 cycles to complete the program. What's the speed up? 2, right? So you the old execution time over new execution time is speed up. So 2. Design B, by the way, is that design B decreases. Design B reduces the number of floating point instruction by half, and the number. So now we touch the instruction count. So this one is rate CPI is still same, and then also what the plus 20 multiply 40%. So what? 40%. So 60% left. So then the 60%. So 10, 20 plus. And then what? Here, also frequency. Frequency is decreased by 20%, right? So 1 gigahertz to the 800 megahertz. So what is actually the performance down also happened here too. So now that is 800 megahertz. So then what? 1 over 8, 800. So the originally it was 1 gigahertz, but now so 1 over 800, 10 to the 6, right? So then the 125, right? So 0 point, no, 1, 2. What's 120? Is that here? Yeah, 1.25 nanosecond now, right? The cycle time is 1.25 nanosecond. So then which is 1.25 nanosecond. So then with design B, what happens? 20, 80 plus 12 plus 40. Multiply 1 to 1 or the 1.25. So then the 120. 92, 132. It's around am I doing why calculation? Yeah, so it looks like it becomes no here. That is correct. I think it's correct. Just the calculation is little somewhat some bad, but anyhow. So this is correct, and then we have to calculate. This is the cycles, not cycles. Now it's distribution time. So this one is just 200 nanoseconds, but this one is some 100 nanoseconds. You just calculate this one, then what we get the actual time, and then so the speed of. If we get the speed of, then what? Again, you must compute the speed of for the design A over design B, not the original. So then we have to compare these two. So what the speed of design A over the design B, then what? Design B's execution time should be here. So this time has to be here, 132, and over 200. So then what? You get some number, and the number is saying that the answer is 1.3333, something like that. That's the answer. Yes?
If you don't mind me asking, I just have two questions for design B.
Mm-hmm.
Could you just go over why you did 40 times 1 on the right-hand side within the parentheses?
This
and
one?
then, no, the last one.
This one?
Yeah.
Here. Floating point, the other. So the others are 40%.
Oh, okay.
And then so like the 45, and then it takes one cycle.
And then also, why was the 800, like, why are you timesing by 1 over 800?
Here, frequency is decreased by 20%. It's 800 megahertz.
But I guess, like, what is, like, the, like, intuition that you would know if you saw a similar question?
So this one is, again, the IC, multiply CTI, multiply CT, right? And then this CT is from frequency. 1 over frequency is cycle time, right? So we have to calculate the cycle time now. So then what happens here is this, right? So then how can we get the cycle time? Originally, this one is also, I just skipped, but what? This one is 1 over 1 gigahertz. But this is just 1 nanosecond, so I just skipped. So, however, here, we have to calculate the cycle time, because now it becomes 800 megahertz. So then what? If you just calculate this, then 1 over 800, this is 800 megahertz, then what? You can get the number like 1.25, I guess. Yes?
Why did you do plus 12? Shouldn't it be plus 120?
This one.
Yeah. Isn't that, you forgot the times by 10.
Right.
Yeah.
Okay, now problem solved. Now that's really good, that's now problem solved. Yeah. Something weird. Yeah, I found it. It's 240 by 105. So then what? So this one is what? 4, 5, right? No, 5 over 4, right? 5 over 4. So what? 60. This is 300 cycles. That's great. Then what? Speed of is So this is the B over A. So 300 over 200. No. And what? This one should be 1.5. It's not 1.363. I think solution is wrong. Is that correct? Yeah, I think this is correct. This one, 42, 80, 80, 40. So this one is correct too. Okay, then 1.5, this is the correct number. Solution I will fix. No, solution is correct too. Yeah, this one. That is correct, 1.5. Do you have a question? So similar types of questions. And then what you see, mistake. Watching your mistake while you are solving the questions. And then also another common mistake is this. Okay, then what? This one, frequency. So what? If I just say that okay, then decreased by 20% to 1 gigahertz to 800 megahertz, then what? Many students just multiply this number directly. So then what? You just multiply here 0.2. I mean 0.8. You just is that no not 0.8, 1.2, right? You just take just multiply by 1.2 here. This is a common mistake. Why? Because you just think some students even do the 0.8. That's completely wrong. You know the 1.2 sometimes. Why you did 1.2? Because the frequency is 20% increased. So what you assume that you have to multiply 1.2. But in fact, what did we get? It was 1.25. Why? Because we calculate this. 1 over 0.8 is not 1.2. It's 1.25. Right? So this is also one common mistake. I'm often see. Do you get this, right? Yes. So when you solve these kind of questions, you don't do some calculation mistake. Okay. So in fact, you solve the problems in your own way. Do I need to discuss this further? Okay. So it makes sense, right? So then the next what we will discuss is a little different issue. So what again, in the processor design, what we have to care the most are the performance. Performance is the most important. Otherwise, people will not use it, right? And but the next problem, next issue is energy issue we have. So what we have to think about the power consumption. What's the power consumption? Power consumption is what power consumption? Do you know the difference between energy and the power, right? So energy consumption is just how much energy is consumed, and then what power consumption defines how fast energy is consumed. Right? Because energy over time is power. So how fast in quantum architecture power consumption is defines how fast we consume energy. So what in fact energy consumption is okay, then it just depends how long you use your machine. So maybe if you run a program, maybe maybe the 10 days, then what? Then compared to you run the program 20 days, you actually consume the half energy. So that's not our the designer's concern. Why? Because how long you use is maybe your issue. I mean, of course, the little we have to think about, but not a major concern because how you use the hardware. However, what we have to care about is power consumption. How fast the energy is consumed in a given time, in a unit time. So there were, when we consider this power trend, we actually consider this equation. However, in fact, this is what this textbook introduces, but this one is not currently right. I will mention that. However, this is the most important equation. So, particularly around this time, 1980s, 1990s, we only care about this. So what a textbook is not completely wrong, particularly when we talk about this time. So then what it want to talk about is this. So what here power consumption is capacitive load. What is this? This is capacitance. Why do we care about this capacitance? Because each transistor has a capacitor, right? So then when we switching, so basically we use the transistor means we actually switching the transistors. And then when we switch these transistors, then what? We actually charge the capacitor inside inside the transistor, right? So then what? That's where we get this capacity load. This is another term is the capacitance. Multiply voltage scale. Multiply frequency. So what? Where this equation comes from is in fact the capacitor energy. So energy consumption of the capacitor is this equation. So what if we have a higher supply, this is what we call supply voltage, by the way, higher supply voltage, and then also we have a higher frequency, then what? Our power consumption increase. So this one is makes sense, right? Because what we have a higher frequency means we are switching the transistors more frequently. And then also what higher voltage, this one you just think in this way. So what if we have a higher supply voltage, then what we are actually use more energy. You can just think in that way. But so then what happened here is this. So our frequency increased here to here is so 1,000 times increased during this time. You can see like what is this one, right? 12.5 to 2,000 now. So what maybe the approximately 1,000 times increase. However, our power consumption does not increase this large. Why? Because we were able to reduce the supply voltage. So then what? The power consumption only increased 30 times. So this one, but so then we actually were able to achieve good performance with less energy consumption. That's what you want to say. So this is what old days we talk about. In fact, what's happening here is, the textbook only discussed that one, but that's not true nowadays. The textbook actually written some decades ago, and then the author actually didn't update it. So what happens currently is this. In fact, when we discuss our power consumption, we actually discuss both dynamic power consumption and the static power consumption. And what is dynamic power consumption and what's static power consumption is this. So what dynamic power consumption is just what I explained. So what a transistor switch, there is a capacitor there, and then when we have to charge this capacitor, and then the energy consumed while we charge this capacitor is defined by dynamic power consumption. Basically, the dynamic power consumption indicates that when we use this processor, how much power is consumed. That's defined by dynamic power consumption. Then what's the static power consumption? Even though we are not using our processor, but still what? energy is consumed. That's we define it as static power consumption. How it can happen? I mean, though we are not doing anything. So what you have to see, though, we have to revisit the transistor again. Here, what is that? This is MOS, right? And then what is gate? There is this is a source, this is drain, and then what? There is this is what is again. This is a metal, and there is we have a capacitor, and then what? This is N type, and P type, right? So this is the MOS, P type. So this is how, and then what? When we use this transistor, what we did, we actually add the supply voltage at gate, here, and then what? Using this voltage, the electricity, we actually create the N-type should be. So what we actually create the channel here, and then what? What happens to the current is this, right? So okay, the capacitor is charging. Once the capacitor is charging, then what? The channel is created, and through this channel, electricity flows. So then what? Dynamic power consumption is coming from here. So when we charge this capacitor, we have to consume energy. This is where the dynamic power consumption happens. Then what? Static power consumption is this. So okay then, we are not using these transistors. So what transistor is idle state. There is no channels there. However, what's happening is this. So still small current actually flows. In fact, the current flows from drain to source here. The small current still flows from drain to source. That's we call static power consumption. Why is this happen? In fact, what happened is that the 1980s, maybe the old days, this current was really tiny. So we were able to ignore. That's why we only care about the dynamic power consumption at the time. However, what's happening now is this. We are making this channel length really short. Now this is just some nano millimeter, right? Nanometer, right? So it's really small. Then what we are observing is this. More and more current flows through this, even though there is no channel, but still what? Because you can just like this common sense, right? Because this is so narrow now. So then what? It's not very hard to close this insulator without channels. So then, which means what? We are now consuming more and more static power consumption. This actually really bothers us. Why? In fact, the dynamic power consumption we can accept because we are doing something. We should pay something, right? So dynamic power consumption is from our transistor switching. So then what we can pay, I can accept that. How much we pay, then maybe matters, but still what we should consume something we know. Static power consumption really bothers us. Why? Because we are doing nothing, but still it consumes energy. And then what is now grow. So this is what we, so what dynamic power consumption is saying, the CV scale F, right? So V is, this is supply voltage again, this is frequency, same equation. Why there is the 1/2 is because we are using CMOS. So what's happening is that, I will briefly introduce this. So there are three types of transistors. One is NMOS, another is PMOS, we learn, right? And then the old days, 1970s, we made a computer with NMOS only. Why? Because NMOS actually operates faster than PMOS. However, using this one type of transistors makes our computer unstable. So then what? The CMOS was introduced around the 1970s, and then what is actually actively used in the 1980s. And then what? Using CMOS, we actually were able to make our computer much stable. But then what's the CMOS? You may ask, right? CMOS is simply a pair of PMOS and NMOS. So in fact, we always use this both NMOS and PMOS together in our circuit. So then what? So it looks like this. You will learn. So then what? Something like something like this. So what? This is the very basic CMOS design, and this is output here, and then what? Supply voltage here, right? So then what? This one is always PMOS, right? And then this one is NMOS, and then so what? You probably have you seen this kind of transistor? This is a CMOS, basic CMOS, and then also what? An inverter also. So, but anyhow, so what we do is this, right? Like we always use both PMOS and NMOS together. So then what happens here is this, right? So then as I said that the channel is charging, capacitor is charging. The channel is created, we consume energy. What about the capacitor? The energy is drained from capacitor. We are not consuming any energy. But since we use CMOS, so what? Either one always create channel, and either one always destroy the channel. So the energy is just drained from the capacitor. So what? We actually consumes half energy. So what? So this C is the constant. So what? Sometimes we can include this 1/2 inside this capacitor 2, assuming that we have half capacitance. But anyhow. So that's all, but this is a more accurate equation. So basically, we are actually, so this C means capacitance of all transistors in the processor. So we have a billion transistors, then what? Each transistor has a small capacitance, right? So then what? We multiply each transistor's capacitance by all transistors. And then what? But we happy because we use CMOS. What's the static power consumption is just this is the equation of the power consumption, right? So I is leakage current, we call leakage current. V is again the supply voltage. What's the leakage current is this one. So what's more current is still the flow through these transistors, ideal transistors. So then what we define this is the leakage current. So then the more current flows through this, then what? In fact, more power consumption happens. So there are some like the power, some questions. Maybe I will go through this. So we have 4 volt and frequency supply voltage is 4 volt, frequency is 1 gigahertz, and then the dynamic power consumption is 3 watt. Frequency is increased to 6 gigahertz. What is the new dynamic power? So okay, then frequency increased to 6 times. So then what? The equation, dynamic power consumption equation, you can just think of this, right? So then what? C V scale F. So then what here? Frequency was originally 1 gigahertz. However, now it becomes 6 gigahertz. It means what? It means this one became a 6F now. So that was originally this one is 3 watt. So what U1 is 18 watt, right? Just 6 times. Why? Because frequency becomes 6 times. I mean so this one is some calculation he does, but eventually it's same thing. So next voltage is 4 volt, frequency 1 gigahertz, dynamic power is 3 watt. Voltage is decreased to 2 volt. What is the new dynamic power? Again, so this equation you think. So that what it originally was 4 volt, but now it dropped to the 2 volt. What happens? So originally it was C multiply 16 multiply F. However, now it becomes C 4F, right? So 4 times reduced. So then what is the new dynamic power? The 3 over 4 watt. Yeah, 0.75 watt. And then processor A has 75% of the capacitance drop of the processor. Processor A also has 20% voltage reduction and 10% shrink in frequency. What is the relative impact on dynamic power? So again, this one becomes 0.75, and also the 20% voltage reduction. So then what? The voltage becomes 3 volt now instead of 4 volt, and then the frequency shrink to 10%. So then what? Now is 0. Frequency shrink is decreased, right? So then the 0.9 gigahertz. So then what? We can just calculate 0.75 9 multiply 0.9. Originally 1 16 1, right? So what this is that's the original. No, this is C. It's actually C. So then what? This is 3. So then what? We have to calculate this C, right? C is 6. 3, 2. This one, right? So then what? So this one is the original C, right? So here, our capacitance is sorry, 16 over 6 over 16, 0.9 multiply 0.9. Where did I get this? First of all, our capacitance I got from original. No. This is the